Now we know how to make a buffer. A lot of calculations involved in actually getting the exact amount of that conjugate base to mix with our weak acid. But now let's kind of just qualitatively look at some of this to see how do buffers work, especially in the presence of strong acid or strong base. When we write buffer equations with the addition of strong acid and strong base, rule number one is that on the reactant side, you've got to have an acid reacting with a base or a base reacting with an acid. You can't have two acids or two bases that would react with each other. There's got to be a hydrogen donor and a hydrogen acceptor. And so in number one, when I write an equation for some general buffer in the presence of strong acid, where this chlorine is a total spectator, but HCl is a strong acid, so it's a good source of hydrogen. The particle that's going to react with the hydrogen should be the base, right? And so there's kind of two ways to write this equation. A real general way is to say, well, for sure, hydrogen, the hydrogen ion, that's definitely going to be one of my reactants. Well, that would react with the basic particle from my buffer, the negative conjugate base. Now, the job of a base is to react with and remove hydrogen. So this good little base, A minus, he should be able to pick up the hydrogen and remove it from the solution. Now, in exchange for the strong acid, I would produce HA, which is a little bit of the weak acid. But a weak acid doesn't fully ionize. So even if I produce a little bit of weak acid, it still is a way of removing hydrogen from the solution. Now, the other way that you might see this written is instead of just writing the hydrogen as H+, you might see it written as hydronium, H3O+. But the equation is really similar. It's still the sign of an acid, and it would react with the conjugate base. The base would take one of those extra hydrogens off the water molecule. That's all hydronium is. So that on the product side, technically, I'd be left with water, and then I would have some of the HA, some of the weak acid. And so either way is totally fine. The key is that I've got the acid, the strong acid reacting with the negative conjugate base from my buffer. On the product side, I'm going to form a little bit of weak acid, but that's not going to have a huge impact on the initial pH because most of the weak acid does not ionize anyway. If I'm writing the general equation for a buffer in the presence of hydroxide, again, that sodium is just a spectator, but I'm for sure going to have hydroxide as a reactant that's being added to the buffer. Well, the base would react with the acid. So this is going to react with the acidic particle from my buffer, the weak acid. Here we're just calling it HA. Alrighty, so the job of an acid is to produce hydrogen. Well, that hydrogen then can react with the hydroxide, and we're just going to form some water. So we can totally neutralize that hydroxide. We can get rid of it. We're going to turn it into water. Now, in exchange for the weak base, I'm going to form a little bit more of the conjugate base. But that is nowhere near as basic as just putting hydroxide in water. So yeah, my pH might go up a little bit, that we're forming a weak base and getting rid of the strong base. So step one is to always kind of think about what the equation is going to look like. If I'm adding a hydrogen, it's going to react with the conjugate base in my buffer. If I'm adding hydroxide, it'll react with the weak acid from my buffer. Okay, so now I'm really obsessed with these particle models, and so is the AP curriculum. They're obsessed with modeling and looking at particle models as a way like, do you really understand what's happening here? Because it's hard to visualize some of this until we break it down to like a particle level. So if the following weak acid and conjugate base were added to the beaker of hydroxide, draw a particle model of the resulting solution, describe the resulting solution. Okay, so in a sense, what they're kind of giving me is a buffer that like this here is supposed to represent like a buffer. It's going to be like a mixture of the weak acid and its conjugate base. And to that buffer, we're adding hydroxide. So I think I'm going to start with the equation. And we're going to do a little buffer stoichiometry. I think this is almost kind of fun. Because after you do this a few times, it's going to totally make sense. Okay, so we're for sure going to have the hydroxide, OH minus. And to that, I would add the weak acid. It's the job of the acidic particle in the buffer to take care of the hydroxide. Donate some hydrogen, turn that into water. Okay, so I'm gonna get rid of that little hydrogen. React it with the hydroxide. I'll form water. And yeah, I'll be left with some A minus, the conjugate base. Ice tables are here to stay. I like to call this the buffer stoichiometry, the BS, because it's kind of what it is. So we're going to count all of the initial particles of everything that we have present. So the OH are these little blue particles. 1, 2, 3, 4, 5. There are 5 of them. And we can do this with particles. I mean, normally we would have like molarities, moles of hydroxide in a liter of buffer. But we can do this with just particles. And then let's see what I got in my buffer. 1, 2, 3, 4, 5, 6, 7, 8, 9 of the acid, the weak acid. And 1, 2, 3, 4, 5, 6, 7, 8, 9 of the conjugate base. And so both acid and base were initially present. A buffer is a mixture. And now the only particle that's kind of left in my equation is the water, and I'm going to keep it in the equation, but I'm not going to use it. So we'll just kind of scratch out the water. Now we call this buffer stoichiometry because it's kind of what it is, in that we don't need to solve for X to figure out the shift. We don't need Q. We just have 2 reactants that do have initial amounts. This is kind of just limiting excess. They're at a 1-to-1 ratio in the balanced equation. So automatically, whichever one is smaller is your limiting reactant. And that we're going to completely react until it's down to 0. So it's going to be the hydroxide. You're going down to 0. I mean, that's the whole point of limiting excess, is that the limiting reactant is completely consumed, and often then at that point the reaction stops. Well, these reversible reactions may never stop, but I'll hit equilibrium. I'll hit a new equilibrium, we should say. Okay, so that's my shift then. We're going to shift forward. These guys are 1-to-1 ratio. So I'll consume 5 particles of the acid. This guy's going down to 4. And this is going to shift up by 5. So this will go up to 14. And we're kind of thinking of it as the limiting reactant is whichever of the initial reactants is smaller. That one goes down to 0. And then it's kind of like the acid is in excess. Fantastic. Well, now if you want to draw all these particles, go crazy, it says draw a particle model, but I think I might just write it. So instead of drawing like 14A minus, I think I'm just going to write in there that here's what's left as this reaction occurs. We'd have 4 of the HA, and we'd have 14A minus. Draw them if your little heart desires. Now, the key is that when I get to this equilibrium line, I still have a buffer. The resulting solution is still a buffer. I still have my weak acid and I still have my conjugate base. It's just that the ratio of acid to base in my buffer has shifted a little bit. So when they say describe the resulting solution, it's still a buffer. However, I've got a little bit more of the conjugate base and I've got a little bit less of the original weak acid. So maybe I'd say something like it's still a buffer, but the pH increases just slightly. Now, if this were like a real solution, let's say it was the acetic acid and acetate buffer, well, then I would have a Ka, and I would do this ice table and use the Henderson-Hasselbalch equation with those final concentrations as my new ratio of acid to conjugate base. Then I would just plug it all into the Henderson-Hasselbalch equation to get the new pH. Aha, isn't that interesting? But the key with a good buffer is that we got rid of all this strong base. That's gone. Yeah, we're going to form a little bit more of the weak base, but it's a weak base, which should have less of an impact on my overall pH. Oh, these are fun. Let's do it again. All right, let's try 4. All right, so in 4, we're going to kind of do the same thing. We've got our initial buffer, and this time we're adding H3O. And we're going to eventually draw a particle model if you want to. Okay, so we are adding this buffer to some acid. So I know then that the H3O plus is definitely a reactant. We're adding it to the buffer. And the acidic H3O hydronium would react with the basic particle from my buffer, the conjugate base. The base should take that extra hydrogen away from hydronium, and we'll just be left with water, and we'll form a little bit of the weak acid. All right, let's ice table this thing and see how it shakes out. 2, 4, 6, 8, 9. So I still have 9 of the conjugate base and 9 of the weak acid, and we have 3 of the hydronium ions, and I don't care about the water. And so it's buffer stoichiometry. When we've got 2 numbers on the reactant side, I don't need to shift by X. We're just going to shift by whichever one is smaller. So it's going to be the hydronium, right? So this guy is going to go down to 0, and everyone else shifts accordingly. 1-to-1 ratio, so you're going down by 3, and you're going up by 3. And so what would be left in the resulting solution? Well, I would have 6 of the A minus, the conjugate base, and 12 of the weak acid. Again, if you want to draw them, go crazy. Now, once I get to this equilibrium line and I want to kind of describe my solution, it's still a buffer. I still have my weak acid and my conjugate base. The solution is still a buffer. However, the ratio of acid and base has changed slightly. So it's a buffer, but now it's a little bit heavier on the weak acid and lighter on the conjugate base. So maybe we'd say something about the pH decreases slightly, ever so slightly. Okay, I can do that. Again, when the pH decreases, that means that it's a little more acidic. And yeah, if we had a Ka value and we had molarities, we would just plug it into the Henderson-Hasselbalch equation and we could solve for the exact pH of the resulting solution. Gosh, this is almost getting fun, right? Let's try 5. All right, we're on a roll. So we've got some more H3O hydronium. That H3O plus hydronium will react with the conjugate base The base should take away that hydrogen, leaving me with just water, and will produce the weak acid. All right, let's count and see what we got here. ICE. Oh man, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the hydronium ions. 2, 4, 6, 8, 9. And yep, 9 and 9. Same buffer. And I don't care about the water. All right, so we're doing some buffer stoichiometry, right? We're going to take whichever reactant is smaller and bring it down to 0. That becomes my shift then. So 1-to-1 ratios means that you're going down by 9 and you're going up by 9. 18. All right, so what's present in the final solution? And if you want to draw them, that's fine. Otherwise, you could just make a note. There would be 3 H3O plus and 18 HA. All right, so let's see if we can kind of further describe the resulting solution. I'm a little concerned about this one. Look at what's left at equilibrium. Oh no, we lost our buffer, right? Uh-oh, here's the problem. We destroyed the buffer. We went beyond the capacity of the buffer. The buffer is supposed to contain the weak acid and its conjugate base, but eventually buffers can only hold so much hydrogen or hydroxide. So I can't go beyond 9 molecules of the hydronium here. And when I do, I've destroyed my buffer. I've gone beyond its capacity. So that now, I mean, in most cases, we wanted the strong acid to be the limiting reactant because then we got rid of it. It went down to 0, and we wanted the buffer to be the excess reactant. So I still had my buffer at equilibrium. It's just that the ratio shifted a little bit. But now we went beyond the capacity of the buffer, and that A minus became my limiting reactant. That guy's gone. And instead, that strong acid is my excess. This is excess strong acid. The other particle that's in the solution is the HA that's weak acid. We obviously don't have the buffer anymore because I don't have any more of the A minus. And in fact, what's left is acid and acid. You've got strong acid and weak acid. So if I want to describe this solution, I might just say it's very acidic. There is no buffer. Not a buffer. That's sad. We've gone beyond the capacity of the buffer. And in fact, now if I wanted to calculate the pH, it would really just be based on the concentration of the excess strong acid. So yeah, you've got strong acid and weak acid, but the weak acid's really not going to dissociate much, especially compared to strong acid. And so your pH would really just be based on the amount of excess strong acid in the solution. So it would be really acidic. Ah, poor buffer, beyond its capacity. All right, now the last little particle model I think is actually kind of interesting. If weak acid is added to a beaker of hydroxide, would the resulting solution be a buffer? So here's something that we'll end up talking about a little bit more in the next section of this acid-base unit, but we've always been told that to make a buffer, you need the weak acid and its conjugate base, or weak base and conjugate acid. That's what a buffer solution is. And that's not wrong. It's just there's a couple different ways you can produce the buffer. Often we produce a buffer by just mixing the weak acid and a salt that contains its conjugate base. But watch what happens here. I've got the weak acid, HA, and I'm going to add it to hydroxide. All right, well, the acid should be the hydrogen donor. So I'd be left with A minus, my conjugate base, and water. Let's say we do a little ice table. Let's see what we got going on here. 2, 4, 6, 8, 9 of the HA, the weak acid. 1, 2, 3, 4, 5 hydroxides. And now here's kind of the difference between this little buffer table and the last few. I'm not going to use the water. I guess that's a similarity. But the difference is that I'm not starting with a buffer. I'm not starting with a mixture of weak acid and conjugate base. Like all the last couple little ice tables, my initial solution was already a buffer. So I had the weak acid and I had its conjugate base. And I do not have the conjugate base initially. But let's play this out. All right, so of my two reactants, the hydroxide is smaller. So this guy is going to be my limiting reactant, and it goes down to 0. Then that becomes my shift. This will shift down to 4. And this will shift up. Check it out. Look at what's left at equilibrium. You've still got some of your weak acid. And even though we didn't initially have the conjugate base, we're going to produce it. And so, yeah, I do produce a buffer. And the key is that, I just can't go beyond the capacity of the buffer. As long as I have less than 9 particles of hydroxide, when I shift everything and look at what's left at equilibrium, I would still have some of my weak acid, and I produce the conjugate base. This is a really tricky question that they'll throw at you on the AP test every now and then, where they'll say, like, would it result in a buffer? The initial solution is not a buffer. The initial solution was just a weak acid. But the final resulting solution, after I get rid of all that hydroxide, that is a buffer. I produce the conjugate base. Aha, tricky. So these buffer ice tables are fantastic. Often we might have molarities, but we could do the exact same thing if we were given molarities. Oh, I love them. All right, so then we're almost to the end. Number 7 talks about a buffer in your blood that's composed of the weak acid, carbonic acid, and its conjugate base, the bicarbonate ion. Normal blood pH is slightly basic, just a little bit over 7, which is far removed from the pKa value, which is fine. It just means that we can tweak the ratio of acid and conjugate base to result in a pH of whatever we want. In this case, we're just a little bit basic. The pH is kept in check by all kinds of mechanisms in your body. The lungs remove carbon dioxide through exhalation. The kidneys can regulate the amount of acid or H3O hydronium in your urine. However, when people have impaired lung function, or sometimes like when they're hyperventilating and they can't exhale properly, we get a buildup of carbon dioxide in the lungs, which then affects the blood pH. And so the reaction that's happening in A is that carbon dioxide, if we can't exhale sufficiently, reacts with water in your body. You're full of water. And we end up forming carbonic acid. Oh, so your body chemistry, your blood chemistry becomes too acidic. How does this affect the buffer balance in the blood? We could just say like it's too acidic. Or it reduces the pH then. And eventually, I mean, there is a buffer in our blood, but we don't want to go beyond the capacity of the buffer, and then we've got some real problems. This term then is referred to as respiratory acidosis, where your lungs cannot exhale sufficiently, and it's really dangerous to have a buildup of CO2 in your lungs, and again, that affects the pH of your blood. It becomes too acidic. And finally, question 8. Why does a mixture of HCl and sodium chloride not produce a buffer? And we've got the acid and its conjugate base, right? Well, kind of. And we've got a strong acid. And yeah, sodium is a spectator, and technically chlorine is the conjugate base. However, the hydrogen from the HCl might do a good job of neutralizing hydroxide, but chlorine cannot neutralize hydrogen. It cannot remove hydrogen from the solution. If chlorine were in the presence of hydrogen, we would just create HCl. And if the HCl is a strong acid, it really means that it's going to like split apart instantly. It's not really going to remove hydrogen from the solution. So the problem is going to be with our conjugate base, chlorine, coming from a strong acid. We don't have a particle in this potential buffer that could really remove hydrogen. Sure, the acid could produce hydrogen and neutralize hydroxide, but we would not be able to accommodate hydrogen.